I'd like to welcome everybody. My name is Bob Bowman, and I'm speaking to you from the Mound Cold War Discovery Center in Miamisburg, Ohio. And today we're having a virtual seminar with our speaker, Kevin Young, out in the wild of Idaho at Idaho National Lab. I assume he's there or somewhere near there. And
Exactly.
he's going to give us a presentation on the use of drones to monitor high radioactivity areas. And so you got a different title than what I saw. But that's okay. And rather than me ramble on, I'm going to turn it over to our speaker, Kevin, and welcome to the Mounds Seminar Series.
Thank you very much, Bob. And thanks to Jack, to both of you, and all the people of the Mound Science and Energy Museum for allowing me to share some of these exciting results that we actually obtained from a historic drone flight. So the title, as Bob mentioned, that you see on the screen right now is called Mission Results, creating a 3D map of a very high radiation confined space using the LiDAR-equipped Helios 3 drone. Also, as we found out later, after we did the mission, it was the world's very first indoor inspection drone flight with LiDAR capability inside a very high radiation nuclear waste storage vault. So we did not even know that we were going for a world's first when we were starting the mission. We were just simply trying to solve a critical problem that the project I work on was attempting to solve. And with all things that tend to be a first of its kind, it takes a lot of people to work together to make these things happen. And so there are plenty of people supporting the team to get this drone flight approved and prepared and ready to go. So I'm going to run right into our little overview here. And I always, as an engineer, I've been an engineer for 35 years now, and we tend to think in terms of problem and solution. And my wife tells me that's not how we should always think, but problem and solution is typically our approach to doing our work. And so the problem we're going to be looking at here that we needed to solve was we needed 3D spatial data from inside a very high radiation location. And there was basically not too many options we had to collect that data. Our solution that we got to was a LiDAR-equipped inspection drone. I'll share the results of that mission. And then if we have time and if there is interest, we can talk about some of the additional efforts that were required to make this happen, because no one had ever flown a drone inside a DOE nuclear waste, high level waste storage vault. And then with the conclusion, here are some of the things we learned and how we're helping other Department of Energy as well as other federal agencies within the United States and abroad to share what we learned to help them solve some of their nuclear waste remediation problems. So what I have here is a highlights video. And there are no words, but there's some fun background music. And this is going to give you visual context for everything we're going to talk about here in the next 30 or 40 minutes or so. And so by having a visual, I found that showing this video right up front really helps people as we move through a more detailed explanation of some of the challenges and how we came up with methods for solving those challenges. So let me play this. This is a kind of a highlights video of the mission itself. Gotcha. Okay, so that gives you a brief overview of the drone flying down into the storage vault. And then that last image you saw was actually an image of the 3D point cloud, or the 3D spatial data that our other engineers in our group were able to take that data. And now we have an accurate model of all the obstructions above those storage bins. And I'll let you know why that's so important here in just a moment. So really what we were looking at were two missions. We wanted to collect the LiDAR data, and once again, I'll tell you why that was important. And that was a complete success. We collected the LiDAR data, and the accuracy was even better than we were hoping for. The second mission, and this was if time permitted, and if there were no other indications to not do this, which was to collect accurate radiation readings or survey readings from within the vault. And we consider that only partially successful. We were able to capture radiation readings, but the drone ended up not making it out of the vault on that third flight. So we did 2 flights of LiDAR. In the third flight, we went in with the radiation survey reading, and the drone, for some reason, couldn't come out. We'll talk a little bit more about that. The good news is we collected the radiation readings that were transmitted wirelessly out of the vault before the drone's battery died. But yeah, as of today, the drone has an estimated 9,760,000 rad of dose. If we ever do get a chance to retrieve it, it's going to be a great science experiment to see how those materials have held up. So let's get down to it. The main problem was we needed a 3D map of a very high radiation confined space. And the location of where this confined space is in the state of Idaho at the Department of Energy Idaho National Laboratory site. And there it is, we're the star, that's southeast Idaho area. And on the site, back in the early 1960s, they built these underground storage vaults, concrete storage vaults. And the purpose of these concrete storage vaults was to store calcined waste. And this is a granular material that is made from essentially the act of spent fuel reprocessing. So the liquid waste that was left over from spent nuclear fuel reprocessing was essentially dehydrated. And the powder that was remained was then put into these storage bins underground, surrounded by 20 inches to 28-inch thick concrete walls. And let's see. So within these 4 bins, there's 4 large stainless steel bins. 220 cubic meters of this calcined material are in those bins. And once again, the mission was to map this area above the bins, because what we need to do per the 1995 Department of Energy State of Idaho agreement is to get into those bins, extract that highly radioactive material, and then get it prepared for shipment to a national high-level waste repository, which doesn't exist right now. That is something that we're working with Department of Energy and the state of Idaho right now, so that our mission is to extract the material, process it most likely by vitrification, turn it into glass solid, and then have it packaged and ready, road ready, to ship out of the state of Idaho by 2035. And this will give you a little bit of an idea what we need to do to get into these vaults or these storage bins. Because when the vault was created, when the storage bins were filled, the Department of Energy had no intention. There was no such thing as the 1995 agreement. The intent was that this waste would remain in those bins in perpetuity until the half-life obviously got to a point where it was no longer a risk. So that being said, there were no engineered methods or no engineered capabilities built into the system to get the material back out. Our approach, the Idaho Environmental Coalition, the group I work with as a prime contractor to Department of Energy, our approach is to robotically place robotic equipment into the vault, robotically cut holes into the top of the bin, and then pneumatically retrieve the material and get it out of the vault and into an area where we can then process it through vitrification. All of this has to be done with robotic equipment that is placed in the headspace. And to do that, this is the number of, we'll call them straws, think of a milkshake, sucking the material out of these bins. We have to drill holes through the top of the vault. We have to place these pipes, these 8-inch pipes, which we call access risers, and then insert the pneumatic retrieval equipment lines down those pipes. What's really important is when we lower the pipes down, we use a robotic welder to weld the pipe to the top of the bin before we send another robot down the pipe to cut into the bin. So we maintain this containment of this fine granular material. We don't want to lose a speck of this radioactive contamination. So the process is very thorough, it's very detailed, but it involves threading the needle through a lot of existing piping and conduits and supports that are currently above the bin group. So that is the purpose for getting that 3D spatial data of every conduit, every support, every pipe above that bin, so that we can thread those pipes, the access risers, down and land them precisely where we need to on top of each bin. And by the way, the 4 bins, you see this little overlay diagram. Each of these 4 bins are actually called bin groups. They have 3 bins within, 2 annular and 1 central bin. That's why we have to lower so many of these access riser pipes, because there is technically 12 bins or 12 cavities that we have to remove the calcined radioactive waste from. So, like I said, identifying the precise locations for each of these access riser pipes is the key for that, getting that spatial data. And we don't want to have to make a mistake when we're drilling holes or in coring holes through the concrete roof. It's one of those things where you want to know exactly before you drill a hole in a high level radioactive waste vault that you're not accidentally drilling the hole in the wrong spot. So all of that hinges on having a very accurate 3D map of the area inside. So now the challenges, all right, here's the challenges. if we could only just get a LiDAR system into that vault somehow, we could collect the data. The problems, and we looked at, actually back in April of 2021, we did an engineering assessment of, all right, how can we get 3D spatial data from inside that vault? Oops, sorry about that. First difficult challenge. That little dotted red square, this is a top-down view of the vault. That little dotted red square is the only opening into the vault. Once again, there was no intention of ever having to do anything other than let this radioactive material decay over time. That little access hatch was there for when they were constructing the vault so that the workers could get in and out as they were finishing construction. And definitely all the workers were out before they started putting in the radioactive material. That hatch opening is only 56 centimeters by 56 centimeters square. Lucky for us, we found a drone, an indoor inspection drone on the market that had a diameter of roughly 48 centimeters. That's the Helios 3 drone. Obviously, at the time we were doing the assessment, we didn't know about the Helios 3. The other challenge we knew we would be facing is a very high radiation field inside the vault. We did not know precisely the radiation level, but our engineers, our radiological engineers, were saying that we could estimate 20 or 10 to 20 gray per hour of gamma, in that environment. And so we said, whatever goes in there to collect this data has to be able to withstand a 20 gray per hour or equivalent 2,000 rad per hour field. We knew too that the air temperature inside the vault is going to be elevated due to the heat generated from the radioactive decay. We had some idea of what that temperature level might be. What you're looking at is a long wave infrared image that we took 2 years before the mission by just simply lowering an infrared camera through that hatch opening and getting this infrared image. We were able to then use FLIR software to calculate the surface temperature of the bin and estimate the air temperature above the bin. And we figured, okay, somewhere between 49 and 55 degrees Celsius is what we would be looking at for air temperature. And then, as somebody put it when we were talking about preparing for the mission, they said, if you put a drone in there, you have to be prepared for a significant amount of dust. They said no one has dusted in there for 70 years. And so we were very hopeful that there would not be any loose radioactive contamination, but we did realize that, yes, there would be maybe paint flake particulate and other concrete dust particulate that would be stirred up. And then, of course, the biggest problem is multiple obstructions. We looked at several different options. We were working on an articulating arm, and other organizations have these articulating robotic arms. And if we could lower the robotic arm through that small hatch opening and then reach out to the areas where we needed to collect the LiDAR, that would be great. The problem with that is that it's about a 25-foot span in the horizontal from the hatch opening to the farthest point where we needed to collect LiDAR data. And that cantilever motion really limited our payload capability for putting a LiDAR sensor in that location. And then there was the number of obstructions that this arm would have had to maneuver around to get the sensor, the LiDAR sensor, in the locations, essentially the four corners of the vault, to collect a complete set of LiDAR point cloud data. So we looked at modifying an existing robotic arm. We talked about designing a new articulating arm or robotic arm that was specifically designed to handle those obstructions. We even looked at, well, could we put a blimp in there inside and fill it with helium? Would that have enough lifting capacity to then maneuver? We talked about maybe drilling multiple holes in the access roof, the vault roof, that we could then lower a fixed LiDAR into those locations. Our nuclear safety folks shut that down right away. They said, if you can find another way, that is what we want you to do. They were not at all interested in drilling holes in the roof, which expose now the areas above that roof to shine paths of radiation through those holes. And then, as it turns out, we're glad we decided to also look at commercially available inspection drones. And that turned out to be the most reasonable approach when we ran the numbers of schedule hit, of a cost for designing a new articulating arm. We said, okay, this is the option that we're going to pursue and see if we can validate for use in this mission. As it turns out, there were only two options available in April of 2021, and that was the Helios drone. And by the way, in 2021, it was the Helios 2. The Helios 3 did not even exist, but they look fairly similar. They're caged indoor inspection drones. And then there was also something called the Sky Crane by another company that was a caged drone. And we knew, due to the tight confined spaces and obstructions, that a non-protected drone would be a much riskier issue for flying. The cage allows you to pinball off of walls and pipes and still remain flying. And so here are just a few specs of the Helios drone. You're looking at 9 minutes of flight time with the battery. It's not a lot of time. That's the issue with the Helios 3 and the Helios 2. The battery weight to size ratio it only gives you roughly 9 to 12 minutes. 12 if you're stripped down maximum. But we figured we only needed literally 5 to 6 minutes of flight time to collect our data. But there's a 4K high resolution camera, protective cage, the oblique lighting. That's where you've got lighting going off in multiple angles. It's absolutely helpful when you're in dusty environments. So the first thing we did, once we decided Helios drone looked like our prime candidate, was we contacted the manufacturer, Flyability, and we had them come out in October of 2021. And the first hoop, the first test, the first validation test we had leading up to accepting this drone as the tool we would put into the vault was a maneuverability test. We said, we need to know, is it able to maneuver in tight spaces? We had a facility out there at the Idaho National Lab, and this is our mock-up facility. We built a mock-up facility inside an existing building so that we could practice all of our technologies for extracting this calcined material out of the storage bins. You can see in the right side, what you're doing is you're looking down on top of a mock-up of one of those bin groups. And then on the left side, it's the scaffolding stairway that leads down into the underground area where we have this mock-up bin. So from a standpoint of how the drone has to fly, like drop down into an area, fly around a bunch of pipes, this mock-up really came in useful for this first test. As it turns out, the Helios 2 was very stable, easy to maneuver. We have two operators that we had identified as our future pilots. Flyability let them take the controls and run this drone. Since we're indoors, by the way, for any of you who are drone enthusiasts, if you're indoors with a drone, FAA does not apply, which is very helpful because you don't even need a Part 107 license to operate this drone. The FAA says as long as you stay indoors, we don't care. So we were able to run this test. We were able to let our identified future pilots try it out. They came back and said it's amazing how stable that drone is. The Helios series of drones uses a series of semi-autonomous stability features so that you can simply let go of the stick both sticks if you're piloting it, and the drone will hover like a stone in the air. Super stable, very easy if you're having to, carefully thread your way through a series of obstacles. So we passed the first test. We were pretty excited about that. Moving on to the next test, because we knew we were going into a radiation environment. Flyability said, we did a little radiation testing like 8 years ago, they said, on the Helios 1 drone. And the Helios 1 drone was the very first in the series of Helios indoor inspection drones. And it had changed so much from 1 to 2 and to 3, because by this time, when we did this test in June of 2022, Helios 3 had just been released. And so the previous radiation testing could not even be considered useful for us. We figured there was enough change in the platform. We had to redo all of the radiation testing. Now, I mentioned that Helios 3 came out in May of 2022. What was exciting about the new Helios 3 is that it was the first indoor inspection drone to have a LiDAR sensor, a lightweight LiDAR sensor made by Ouster. Helios 2 worked with photogrammetry, so you could still collect 3D spatial data using camera techniques of photogrammetry, but the resolution that flyability indicated with the Helios 3 and the LiDAR would be much greater. So we knew that flyability had let us know under an NDA that we signed with them back in late 2021. They said, LiDAR's coming out. We'll work with you under NDA. We don't want you to let anyone know we're doing this until we release it in May of 2022. And we said, great. So we prepped everything. We got our testing lined up. And in May of 2022, when Flyability started selling the Helios 3, we were their first customer to buy an Helios 3, which we then promptly destroyed in radiation testing. So their very first one, we put to death by gamma ray. But absolutely important. We could not take the risk of running this mission without knowing how the drone would behave in a radiation field. We partnered with Idaho State University in Pocatello, Idaho. They have the Idaho Accelerator Center, where they have these large high-powered accelerators and large high-powered X-ray generators. And what we were able to do was do our testing with a X-ray generator, one of their X-ray generators, that had the capability of generating 450 keV gamma or photons if it's X-ray, but basically the same, very close to the same type of radiation we would expect to see in the vault in terms of energy level. The primary component of the calcine is cesium-137, which has 662 keV energy. So 450, 662, we figured it would be close enough for us. So we went down in June, we took the Helios 3, we hovered the Helios 3 in front of the X-ray generator and simply blasted it during 6-minute flights. And we stepped up the radiation over time. We wanted to find out where the threshold was, so we just didn't hit it with the highest amount right away. We started low at 600, or I should say 6 gray per hour. We'll stay in gray per hour. 6 gray per hour, and we did a couple 6-minute flights. So it would hover for 6 minutes in front of the radiation, and then we would turn off the X-ray generator. We'd go back into the vault, and the pilot, Flyability had a pilot for us. They would then do a flight untethered around the vault, and you can see a little photo of one of those flights, to just check out all of the vital systems on the drone. And while we were hovering the drone, we were able to observe it from a closed CCTV or PTZ camera inside the vault. as well as we receive a continual stream of the drone's vitals that come to the pilot's ground control station. So we're able to track it, watch it carefully to see if there were any anomalies due to the radiation. And we kept doing test after test after test, and we're about, if you see the graph, that kind of shows you the step up in terms of radiation and the number of 6-minute flights. We did a total of 19 6-minute flights, with the last flight we did, successful flight, was at 1,000 gray per hour, or 10,000 rad per hour, which was far in excess of our threshold of 10 gray per hour. That's what our test team said. All right, if the drone can survive 10 gray per hour and a total cumulative dose of 10 gray, then we figured that was a good enough indication for us to then move forward and say, we're willing to take the risk in terms of radiation, that this drone's going to do its job and fly the 6 minutes we need inside that vault to collect the radiation data. So very successful in terms of radiation, passing our test requirements. After flight 19, the pilot did its untethered flight around the X-ray vault area. Everything looked great. No problems. We didn't see any indications of problems. We powered down the drone. We downloaded all the data, the metadata, which gives you additional information. And then we switched batteries. And once you switch batteries, you have to then reinitialize to do another flight. And when we tried to reinitialize, the drone would not reinitialize. And it gave us an onboard computer memory fault. And we didn't know if it was exactly what the problem was. We just know that we tried everything to get past that fault. No dice. So basically our testing, our rad testing, ended there. And months later, flyability, we sent the drone back to flyability. They did a post-mortem on the drone, and they realized that it was the SD card that is used for onboard computer memory that failed. So it wasn't the LiDAR. It wasn't the 4K camera. It wasn't the radio transmission system. It wasn't the semi-autonomous stability features. All of those continue to work fine. It was simply the SD card that is embedded inside the drone that failed due to radiation. All right. By the way, that green dotted line, once we passed that, everyone in the control room cheered, because we knew that was our threshold for a go, no go to continue using the Helios 3 or testing it. And it did wonderfully well in radiation. So since we knew that collecting radiation survey data was going to be part of the mission, and our radiological engineers really wanted this accurate data from inside the vault. And the reason that's so important is because our project is going to involve installing robotic equipment inside the vault. So for design input, to ensure that our robotic equipment is going to operate correctly, to know the precise radiation levels in the vault, very helpful from that perspective. And then also from a worker's safety, a worker's stay time, a worker's estimated dose. As they are getting close and installing this equipment, there's always a little bit of dose that would be received in these situations. And by knowing the precise values of the radiation fields inside the vault, our rad safety folks can plan the procedures and safety protocol and know how much shielding we need in certain areas. So very important data to move forward and bring down the cost and risk of the program. Because if we don't have accurate data, we have to assume the worst case, and then we have to shield accordingly. So the data, knowing the precise fields, very helpful. We had flyability come back out, because after we successfully passed the radiation testing, flyability said, we are working on a new configuration of the Helios 3 drone, where we're going to attach a Mirion RDS 32 wide range electronic dosimeter. We're going to integrate the data stream from that electronic dosimeter so that the information is transmitted back to the pilot's ground control station, and that radiation data is then embedded in the 3D spatial data also that is collected by the LiDAR system. And so our radiological engineer said, yes, that would be great. We would love that feature. What we did at that point was we worked with, in a collaborative agreement with Flyability, to develop this prototype configuration that included the dosimeter. And actually, when we flew the mission, that configuration was still prototype. It had not been released to the public yet. So we knew we were accepting a little bit of risk in terms of flying the mission with the dosimeter on it. But back in August of 2022, we said, show us what you got. They brought their prototype with the dosimeter. We had our RadCon engineers set up a cesium check source out there. And you can see that yellow circle on the left of your screen. That's the drone hovering over the check source and getting the radiation readings. Our pilot on the right and our rad engineer there right next to him, they're looking at the readout of the survey radiation information to make sure that it is accurate and it's easy to read and it's coming up with the correct information. On your left is the Helios 3 with the prototype. They simply have a couple Velcro straps holding that dosimeter in place with a custom cable you can't see, but the custom cable plugs into the main body of the drone. On the right, this is an image that was returned by the drone looking down inside the pig or the shielded container of the cesium-137 check source. That's a view, by the way, that not many people get to see, is looking down at a radioactive check source. But the results were positive. The maneuverability with the added weight of the dosimeter, which is about 220 grams, was acceptable. Pilots reported, yeah, it's a little sluggish. It's a little sluggish compared to just the LiDAR system on board, but they said it's still maneuverable. And so we were like, all right, we passed another hoop in our testing. The last thing we wanted to do in terms of validating the platform was to do a high ambient temperature test. The manufacturer, Flyability, said our upper limit that we're going to claim is safe is only 50 degrees Celsius, is what they said would be the upper limit. We were estimating we would be slightly above that at 54 degrees Celsius. And so Flyability said, you should do your own testing to verify that you're going to be happy with the performance of the drone at that elevated temperature. So we got an environmental test chamber, put the drone inside. The main thing we were concerned about, based on what the manufacturer reported, was that the first thing that's going to overheat in a high temperature environment are the motors, the four motors. This is a quadcopter drone. And these motors are pretty high-end motors. They spin very fast because of the size to weight ratio of the drone. They have to spin fast to keep that lift. And then, so for stability purposes, when the drone pinballs with the cage, the motors have this capability of rapid reverse. They can rapidly reverse direction. So that being said, the motors are working really hard. That's the area we had to watch. The telemetry that comes back to the pilot includes each motor temperature. This was perfect for our test. So what you see on the right is the orange dotted line that cuts across horizontally across the center of the graph. That is the ambient air temperature inside the test chamber. And it basically levels off just below 55 degrees C. The four other graph lines you see are each of the motors. And according to Flyability, they said your motors will be fine. The safety features on the drone will not kick in and cut off your motors until you reach 95 degrees Celsius. If you exceed 95 degrees Celsius with a motor, then the onboard software will automatically reduce the speed to a point where the drone might just land on its own. So we were very much watching our graphs as they leveled out, and luckily all 4 motors leveled out below 95 degrees C. Not much, but below that threshold. We felt that this test validated the drone in terms of its high temperature performance that we would expect to see. So we finally passed the last validation test in October of 2022. What was left is a quick training of our pilots. No one had ever flown this mission before. This involved dropping down through 2 hatch openings and into this 25-foot by 25-foot vault to complete this mission. So we set up a simulated control room. You can see on the left, we built these stainless steel replicas of the hatch openings that the pilot would have to fly through. We even put a box fan under the lower hatch opening to simulate the thermal updraft that the pilot would expect to encounter as they were dropping down through this hatch opening, and all that warm air, due to the radioactive decay, was moving up out through the hatch opening. And this gave our pilots, we had a primary and a backup, ample opportunity to practice flying this mission and get it down in time where they were well within the safety margin of battery life. I don't know if you ever saw Top Gun Maverick 2, but there's a scene in that movie where they have to train and simulate to make sure that they do their mission in time. And so we nickname our primary pilot Maverick, which he to this day, that's his nickname now. Let me give you a little idea of the team that we put together that would be doing the mission. There's the pilot, there's the spotter who would be looking at cameras that we lowered into the vault to observe areas around the drone, the system engineer, and then we had one person whose sole job was to watch motor temperatures and then also look for any other error codes that might come across the telemetry. So we had telemetry, systems engineering, pilot, and spotter. I'm going to run this as a quick little video from one of the flights with the dosimeter on board. And it's sped up. It's 2 times speed, so we can move through this rather quickly. But it shows you, from the drone's point of view, the path that it has to follow. And if you remember the video at the beginning of our talk, this is pretty much what's happening. You're dropping down, you're getting buffeted a bit by some updraft, and now you've got some outlines on the floor that represent the 4 bin groups. The pilot then practices going to each of the assigned LiDAR data collection points and then returning back to base and making sure that they do that all in the appropriate time before battery life is expended. So on the day of the mission, we had to set up a tent around the hatch opening so that we would meet FAA requirements and remain indoors at all times. Even the 5 seconds it took us to lift off and then drop into the vault had to be in a covered environment. So we built this, and you can probably best see it in the center photo there, that white tent with clear poly windows, plastic windows. And then we also had a hatch opening in the roof so that we could lower, or first of all, remove the concrete hatches. These things weigh upwards of 2,000 pounds. And then also lower in what we call the mission support boom, or the MSB. And this boom had the pan tilt zoom camera, it had some lighting on it, it had, most importantly too, it had what we call a range extender antenna. This antenna allowed for a secure RF link with the drone while it was in the vault. So we were able to basically drop an antenna down with this boom, which then ensured that as the drone was flying around inside the vault, it had very solid RF communication. And the boom also had, well, the boom was going to have a temperature sensor on it. And as it turns out, due to some complications, we literally had to lower that down a thermocouple on its own wire, basically like a fishing line, into the vault to collect ambient temperature readings. There's a picture of the tent highlighted in yellow. That big blue tent, that's our command and control center. That's where we had some of the large screen monitors, and our pilot sat in that area. Just for perspective, this is where the vault is. We're almost literally on top of the vault, but due to the amount of earth and concrete, we're shielded from the radiation at this point. Now, as soon as they pull the hatch openings off, that area right above the hatch is getting a pretty good shine of radiation. So no one is permitted into that envelope. So there's one of the hatch covers, the mission support boom. Here's our thermocouple Type J wire that we lowered with a little black weight on the end of it. And we took our thermocouple readings after the hatch opening, and this will play into the reason later on. I'll explain a little bit more when we could not get the drone out. But the temperature readings we saw were just slightly elevated above 40 degrees C, which was due to all the cold November air in Idaho rushing into the vault at the time. As it turns out, over the course of the first two flights, the air inside that vault was heating up, and we had no way to measure that. And we think that played into the loss of lift on the third flight. Anyway, we had a flight plan. Go to each of these numbered locations, collect your LiDAR data by spinning the drone on its Z-axis so that all areas in that locale are painted by the LiDAR laser pulses coming out of the drone. Move on to the next, move on to the next, move on to the next, and then come back out. We did two flights. The first flight was about 4 feet or 1.2 meters above the surface of the main surface of the bins. The second flight was about 4 feet below the roof of the vault. And this was to ensure a complete data set of coverage. We probably had a complete data set on the first flight. The second flight was more of an insurance flight to just make sure we didn't have any gaps in that 3D map. The LiDAR, each flight, the first one took our pilot, he was being super cautious, 7 minutes and 10 seconds, and had about, I think, 12%, less than 12% of battery life. The second LiDAR flight was 6 minutes and 12 seconds. I'm sorry, first was 7 minutes, 10 seconds. Second flight was 6 minutes, 12 seconds. Inside the control room, we had experts from both Flyability and a company called GeoSlam that deals with the 3D mapping software. Our goal was to have the GeoSlam expert do a quick review of the data that we collect and tell us whether we got a complete data set or not before we go through the very cumbersome effort of putting those concrete blocks, hatch covers back in place and sealing up the vault. If we had to fly the drone in again to catch some missed areas, we wanted to know that from the software expert before we closed up the vault. But the quick data look was great. They said you got excellent data, and as the radiation flight, now this is flight number 3. We added the dosimeter, an extra 220 grams. The air inside the vault has now been increasing in temperature. When the flight took off, third flight, they were above hatch number 1, basically at ground level. The pilot flies the drone up, literally up, over the handrail and down into the vault. As soon as Chad, our primary pilot, passes that lower vault, I'm looking over at him and he has this really bad look on his face. It's like, something's not right. And he's telling me, I can't maintain lift. I've got sticks full forward, and the drone continues to just slowly settle down. And it actually landed, luckily, it landed on top of a bin as opposed to going all the way down to the bottom of the vault. So it landed on the bin. Everything that we tried to do with the input and advice from the manufacturer's expert who was in the control room at the time was to no avail. We could not lift that drone off. And eventually the battery died. And the drone sits where you see its final resting place is on, I believe that is bin group 3. But the good news is during this whole time, the radiation readings, the survey data was being transmitted out. So we actually received very accurate radiation reading during this time. So we collected our LiDAR data, we collected our radiation data, we met those two objectives. The only thing we did not collect was our drone back. We didn't get our drone back. And based on the value of that data, luckily our managers were fine with this. They knew this would be a risky endeavor. And as it turns out, we had planned for this potential occurrence. Nuclear safety did an assessment, a detailed assessment of what would happen if you leave the drone in there, what kind of effects would the lithium ion battery have, if any detrimental effects. And the results of that very detailed assessment was that leaving the drone in the vault posed no risk to humans or the integrity of the storage bins. So we knew this was a possibility. It happened. We had done our homework ahead of time, and no issues there. The good news, we collected great data. The software allows you, I'm going to run this little video, software that Flyability has allows you to do a quick review of your data. So on your left, you've got your point cloud. On your right, you can replay the video from the mission. And what's interesting is the video will play, and there's a little avatar inside the 3D model that's flying around that's showing you exactly where you are in your asset, or in this case, our storage vault, and what you're looking at. And in complex environments, this kind of software is extremely valuable for knowing how to, what exactly you're looking at, where your points of interest are. So we were excited. That was very helpful. Here's a map of elevation map of the radiation readings. The maximum elevation reading was, of course, at the top of the bin where the drone sat as it was trying to get back off the ground. And that ended up being only 7 gray per hour, much less than the 20 gray per hour worst case we estimated. And so that in itself was an excellent bit of information. So that really helps reduce the cost for shielding and expense for hardening the robotic equipment. So excellent design input there. That is the end of our mission, and I've got some other slides here that where Department of Energy is looking to use this type of platform or a similar platform, because now we are starting to see other companies coming out with indoor inspection drones. And being a DOE prime contractor, we don't promote one over the other. So the results that I give you about the Helios 3 are the results I know about from our testing. And there are other drones that are coming out in the market that I'm sure will be very valuable tools for these nuclear waste remediation projects that are all part of the Department of Energy EM mission. So at this point, Bob, Jack, if it's okay, I'd like to take some questions before it gets too late, and then we can use these additional slides as necessary if they come up.
You've been up here for the while, and thank you, Kevin. It certainly was an unusual high tech, not like they make in the movies, but kind of like what real world takes to do this. So you counted the radioactivity. Does it matter what it's all gamma that you were monitoring, and
right now the calcine does have some screaming beta involved, but since all of the radioactive material was contained inside the stainless steel bins, the beta, of course, was not an issue for us. Now, once we cut into the bins, we know we have to deal with the beta. But for this mission, gamma was strictly our challenge.
Okay. And so able to map and do the geometry of all that would help. I would assume your operator might have played a little bit, learning how to fly drones and so forth before he got this job.
The reason our primary operator got the nod was that before he came to work for the Idaho Environmental Coalition, he worked for Idaho Falls Police, and he was the one that ran their drones occasionally. He made sure we knew that. He said, I don't have a lot of, I don't have a lot of experience, but I've flown one or two. I've never flown one of these cage drones, but once he had the opportunity from a flyability demo to try it out, that's one of the strong points about the flyability Helios 3 is that it's a very short learning curve for a pilot. And the reason is because the stability features are so good that if a pilot gets into a nervous situation, like I can't remember which way is left or right or up or down, they just let go and the drone stops right where it's at and it hovers. If it was moving forward, it puts on the brakes and it stops right where it's at. And then the pilot can collect their calm and then continue on.
Seems like the drone might be smarter than the operator on how it manages itself.
It's pretty impressive.
Do we have any particular question from somebody in our audience here that would like to come up and say anything?
Can you hear me?
I sure can.
This is Dave Ballsmeyer. What was the half-life of the material in that tank?
Oh, Dave, I can tell you it's cesium-137, and that is one question I have not been prepared for. I apologize for that. If our
I have the answer.
Somebody has the answer?
30.05 years.
Okay, perfect. Thank you.
So,
Thank you, Jack.
so how long would it take for it to become safe if we didn't spend $1 on doing anything except keeping it there?
From what I understand, we're in terms of it was hundreds of years, and I don't know the exact point where Department of Energy or State of Idaho, would say, okay, we're good enough to now we're going to cap it. We're gonna put a bunch of concrete over the top of this, and it's like low enough radiation level now where we can say it's unattended. Cap it and consider it safe. I don't know the exact number, but I do know it's in the hundreds of years.
So has anybody done a life cycle comparison of what you're going to do with just capping it?
Yes, there have been a lot, and I am not. I'm more on the engineering side. I'm an electrical engineer, and I live in the world of engineering. But in the program world, at the upper level, especially where strategic decisions are made in terms of how money is to be spent, yes, those analyses have been made. But here's the kicker: is that 1995 agreement with the state of Idaho
Yep.
is holding our feet to the fire. And as far as I understand, the state is not moving off of that.
It's a political decision, in other words.
Right. I'm an engineer. I am very happy to stay away from that stuff. I'm glad we have people who are capable of maneuvering in those areas, but that's not luckily something I have to deal with.
Well, DOE has an image to maintain, and politics does seem to be a #1 priority to them.
I am not going to argue on that point. I think actually any organization is probably concerned with their image, and yeah, it's a challenge. This is a difficult challenge. I've heard many of the reasons why it would be best just to leave it there. So a lot of people think that is the appropriate path forward. A lot of people, though, also think that there's the Idaho Falls or the Idaho Aquifer underneath this area, and any kind of accident or issue that would cause this material to get into the aquifer would, of course, be devastating. But like I said, these are areas that I listen to. I'm in tune to, but I don't. That's above my area of expertise.
Okay, thanks, Kevin. Is there any other questions on aspects that were presented here? I don't see anything, Jack, popping up. Oh, you got one? Yeah, come on up. Because I don't think you can.
Just stand here.
Okay, right there.
Okay.
Oh, they told us. Okay.
Hey, Kevin, Jim Fountain, retired DOE. Got a question on the drone. You
Okay.
talked about you flew it 3 times. Third time it died. It's sitting on a canister. I'm curious about radiation and handling of the times first, second, and third, where you said you changed the battery. You didn't talk too much about how the drone was handled protection-wise in between those 3 times. Can you add to that at all?
Absolutely. No, that's an excellent question. And there are so many angles or so many parts of this mission. That was one I didn't have in the lineup. But what we did, because we were told that there is a possibility that there is some of the calcine material loose outside of the bins from their filling and like sampling efforts. So we went in with this approach that we have to assume the drone's going to come out and have some contamination on it. So that tent that was built for primary purpose of FAA also served as a barrier. I'm not going to say it's a radiological barrier, but a barrier that we actually had our RADCON techs ready with glove port pass-throughs. And the first thing they did when that drone came up is they approached the tent with a rad meter. Then they went in, they took swipes. They verified that the drone swipes came up negative for radiation. And then after that, then still using the glove port, they plugged in the USB cable that allowed us to download the high resolution data, camera data, and the high resolution LiDAR data. A smaller set of that had been streamed out to the controller's tablet, and then also changed the battery for the other flight. So yes, we were taking precautions just in case the drone did come up contaminated. Now, if that drone were to get contaminated, the manufacturer and our radiological techs and engineers all agreed that you really could not effectively decontaminate it. So at that point, your choice was that, hey, we knew if we had to fly another flight, we had the means to make these switches and swaps all within this barrier, and so we could at least collect the data, still continue the mission, collect the data, and then the drone would be bagged and taken off, never to be seen again by our RADCON techs, probably. But yeah, great question.
It's good. So one of the other options, you're talking about Savannah River and Hanford. Are they close to considering using drones to monitor their situations?
Absolutely great. That I'm glad you did that, because I was very excited when I put the slide together. It was earlier in the spring. And all of these places, the Waste Isolation Pilot Plant in New Mexico, Hanford up in Washington, Savannah River, all of these places, their engineers contacted us after we flew our mission in November of 2022. And they were saying, hey, we've got these other applications where, we're going to need to fly in a radioactive environment. And I was super excited that the Waste Isolation Pilot Plant, they finally flew a Helios 3 on May of 2024, just not too long ago, into an area, one of the tunnel areas that had been considered compromised in terms of safety, and no one had been in there for 10 years. And so they used the drone to fly into this area and inspect the walls and take amazing high resolution video and photos before they then were going to follow up with sending some human inspectors.
So with that situation, then would they also get the radioactivity level data from the drone as well, or was it mostly the LiDAR images
Right.
of the?
No, and it's a choice. It's a choice. Now the mission that flew in WIP just last May, they were strictly visual. They did have LiDAR on board. They did have LiDAR, but their interest was in the visual data and snapping images and collecting the high 4K resolution video.
I mean, I would assume that if you could then monitor the radioactivity, you could isolate an area where you would focus attention on or stay away from if you could.
Exactly. And for WIP, that in that area, they knew that the radiation was not a concern. It was more about the structural integrity of the walls. Yeah. And so they didn't even fly with the dosimeter on, because if you don't need the dosimeter, you increase your flight time by like a minute and a half.
And
just
and
by
that's a
not-
big percentage, right? So that,
It is. So yeah, and as we found out, we found the flight envelope of where the excess weight of the dosimeter and then the heated environment, we basically just exceeded the flight values, the air temperature. Any of you are pilots, air temperature is a critical factor for flight and weight. So weight and air temperature. And we found that boundary. We can't say 100% for certainty. That's why we lost lift. But that is, we had no other indications, no other failure error codes coming back on telemetry. So we think we just exceeded the weight and air temperature. So yeah, if you don't need that extra weight, don't fly it.
yeah, don't do it. Get the information you need as much as you can. But it's really an interesting story and most people wouldn't have heard about. And the fact that old school techniques have been displaced in spite of the fact that I grumble about 21st century technology. This is really a way to implement that as we deal with a major problem or major situation that's going to last for a long time and what remediation can do. So Kevin, I really appreciate your time. Let's give him a round of applause. We do have several people here, so hopefully you will hear that.
I do. I hear it in spirit right
I don't
here.
know if the others will do that for you, but again, thank you so much for preparing this and sharing information.